My 5-year-old son asked me today if there were a kind of a fireman's pole from the moon down to the Earth. How long would it take to slide all the way from the moon to the Earth? First, let's get a few things out of the way. In real life, we can't put a metal pole between the Earth and the moon. The end of the pole. Near. The moon would be pulled toward the moon by the moon's gravity, and the rest of it would be pulled back down to the Earth by the Earth's gravity. The pole would be torn in half. The Earth's surface spins faster than the moon goes around, so the end that dangled down to the Earth would break off. If you tried to connect it to the ground, as a professional driver on closed course, do not attempt. There's one more problem. The moon doesn't always stay the same distance from Earth. Its orbit takes it closer and farther away. It's not a big difference. But it's enough that the bottom 50,000 kilometers of your fire station pole would be squished against the Earth once a month. But let's ignore those problems. What if we had a magical pole that dangled from the moon down to just above the Earth's surface, expanding and contracting so it never quite touched the ground? How long would it take to slide down? If you stood next to the end of the pole on the moon, you would have a problem. You'd have to slide up the pole, and that's not how sliding works. Instead, you'll have to climb. People can climb poles pretty fast. World record pole climbers can climb at over 1 meter per second in championship competition. On the moon, gravity's much weaker, so it will probably be easier to climb. On the other hand, you'll have to wear a spacesuit, so that will probably slow you down a little. If you climb up the pole far enough, Earth's gravity will start pulling you down. When you're hanging onto the pole, there are 3 forces pulling on you. Earth's gravity pulling you toward Earth, the moon's gravity pulling you away from Earth, and centrifugal force from the swinging pole pulling you away from Earth. At first, the combination of the moon's gravity and centrifugal force are stronger, pulling you toward the moon, but as you get closer to the Earth, Earth's gravity takes over. The Earth is pretty big, so you reach this point, which is known as the L1 Lagrange point. While you're still pretty close to the moon, this is definitely a dream I've had. After another few weeks of gliding along the pole, you'll start to feel gravity take over, speeding you up faster than you can go by pushing yourself. When this happens, be careful. Soon you'll need to start worrying about going too fast. As you approach the Earth, its pull will start to increase your speed quite a bit. If you don't stop yourself, you'll reach the top of the atmosphere at roughly escape velocity, and the impact with the air produce so much heat that you risk burning up. Spacecraft deal with this problem by including heat shields, which are capable of absorbing and dissipating that heat without burning up the spacecraft behind it. Since you have this handy metal pole, you can control your descent by clamping onto it and controlling your rate of descent through friction. There may not be any sound in space, but you'll feel it conducted through your bones. Make sure to keep your speed low during the whole approach and descent, and if necessary, pause to let your hands or brake pads cool down, rather than waiting until the end to try to slow down. If you get up to escape velocity, and then at the last minute remember that you need to slow down, you'll be in for an unpleasant surprise as you try to grab onto the pole. At best, you'll be flung away and plummet to your death. At worst, your hands and the surface of the pole will both be converted into exciting new forms of matter, and then you'll be flung away and plummet to your death. It's fine. I brought some oven mitts. Don't worry about it. The moon orbits around the Earth at a speed of roughly 1 kilometer per second, making a wide circle every 29 days or so. That's how fast the top end of our hypothetical fire pole will be traveling. The bottom end of the pole makes a much smaller circle in the same amount of time, moving at an average speed of only about 35 miles per hour relative to the center of the moon's orbit. 35 miles per hour doesn't sound too bad. 35 miles per hour doesn't sound bad. Fortunately for you, the Earth is also spinning, and its surface moves a lot faster than 35 miles per hour. At the equator, it can reach over 1,000 miles per hour. 1,000 miles per hour does sound bad. Even though the end of the pole is moving slowly relative to the Earth as a whole, it's moving very fast relative to the surface. Is it just me, or is the atmosphere piling up in front of the pole? Is it too late to turn around? Asking how fast the pole is moving relative to the surface is effectively the same as asking what the ground speed of the moon is. This is tricky to calculate because the moon's ground speed varies over time in a complicated way. Luckily for us, it doesn't vary that much. It's usually somewhere between 390 and 450 meters per second, or a little over Mach 1, so figuring out the precise value isn't necessary. I don't see what you're so worried about. Let's buy a little time by trying to figure it out anyway. The moon's ground speed varies pretty regularly, making a kind of sine wave. It peaks twice every month as it passes over the fast-moving equator, then reaches a minimum when it's over the slower-moving tropics. Its orbital speed also changes depending on whether it's at the close or far point in its orbit. This leads to a roughly sine wave-shaped ground speed. Do not use this graph for planning purposes. It's not that it isn't accurate, it's just that any kind of plan that involves this type of data is probably a bad one. Well, ready to jump? There's always something else to calculate. The moon's orbit is tilted by about 5 relative to the Earth-Sun plane, while the Earth's axis is tilted by 23.5. This means that the moon's latitude changes the way the sun's does. It's moving from the northern tropics to the southern tropics twice a year. This is part 2 of our story about sliding from the moon to the Earth. If you haven't read part 1, you might want to go back and start there. You start by running on the moon to build up speed, then use a pole to slide all the way down to the Earth. Our protagonist starts his run up in a few seconds, then takes a deep breath and leaps onto the pole. The moment he leaves the moon, he begins plummeting toward the Earth. He needs to get to the ground fast, but he also needs to survive the trip. So what should he do? However, the moon's orbit is also tilted, and this tilt rotates on an 18.9-year cycle. When the moon's tilt is in the same direction as the Earth's, it stays 5 closer to the equator than the sun, and when it's in the opposite direction, it reaches more extreme latitudes. This means our protagonist's pole is going to be moving faster or slower depending on where it is relative to the Earth's surface. When the moon is over a point farther from the equator, it has a lower ground speed, so the lower end of the sine wave goes lower. Here's the plot of the moon's ground speed over the next few decades. The 2020s will have the lowest average moon speed of any decade in my lifetime. A new contender for the least consequential thing I've ever learned. The moon's top speed stays pretty constant, but the lowest speed rises and falls with an 18.9-year cycle. The lowest speed of the next cycle will be on May 1st, 2025. So if you want to wait until 2025 to slide down, you can hit the atmosphere when the pole is moving at only 390 meters per second relative to the Earth's surface. If you're reading this before May 1st, 2025, please pause your reading until that date, then resume at the next paragraph. When you do finally enter the atmosphere, you'll be coming down near the edge of the tropics. Try to avoid the tropical jet stream, an upper-level air current which blows in the same direction the Earth rotates. If your pole happens to go through it, it could add another 50 to 100 meters per second to the wind speed. Regardless of where you come down, you'll need to contend with supersonic winds, so you should wear lots of protective gear. Make sure you're tightly attached to the pole, since the wind and various shockwaves will be violently battering and jolting you around. People often say, it's not the fall that kills you, it's the sudden stop at the end. Unfortunately, in this case, it's probably going to be both. At some point, you're going to have to let go of the pole. It's for obvious reasons you don't want to jump directly onto the ground while moving at Mach 1. Instead, you should probably wait until you're somewhere near airline cruising altitude, where the air is still thin, so it's not pulling at you too hard, and let go of the pole. Then as the air carries you away and you fall toward the Earth, you can open your parachute. We'll wait here. Next window is in the early 2040s. Then at last you can drift safely to the ground, having traveled from the moon to the Earth completely under your own muscle power. That's one large, supremely complicated and unnecessary sliding and falling and tumbling step for a man. One giant but equally pointless leap for mankind. In retrospect, we could have just made the magic pole lengthen and shrink to avoid hitting anyone. But you can't spend your life looking backward.